Hi, this is Miguel Zumalacarregui at the Max Planck Institute for Gravitational Physics, and I'll be talking today about gravitational waves and new effects that appear in gravitational lensing in theories beyond general relativity. This is a work that will appear hopefully in the coming weeks, and I've done together with Jose Maria Chiara. The motivation to go deeper into gravitational wave lensing is that standard gravitational lensing is already one of the most robust and rich probes of fundamental physics that we have at our disposal. In particular, it's a very strong test from GR, since very early historical tests like the light bending. And in later times, through the understanding of the cosmological propagation of gravitational waves, so not lensing, just modified gravity effects on the Friedmann-Robertson-Walker homogeneous background, we have been able to test theories of gravity very well. In particular, we know the different effects that might arise, and the speed turns out to be a very constraining probe of theories of gravity. But this propagation in the average universe is it's a little bit boring, and it's because there are only 4 terms that can modify the gravitational wave equation. So one reason to study gravitational wave lensing is because the inhomogeneities in the universe will break the simplicity of this equation and will introduce new effects. And another reason is that we are going to obtain a lot more new gravitational wave events. You can see here the cumulative count of candidate events from LIGO's first operational runs. And this abundance of events will allow us to probe deviations from the average universe. So you can think of strong lenses and other events that perhaps generate in non-typical regions of the universe that might help us test fundamental physics. Whereas from until we have new detectors like LISA, we're not going to qualitatively learn anything new from this average Friedmann-Robertson-Walker propagation. So in a nutshell, what I'm going to present in the next few minutes is a new framework to study gravitational lensing of gravitational waves beyond GR, in which, in general, so I'm going to focus at leading order and focus on the effects that have to do with causal structure. And the main effect is that the gravitational polarizations that we're used to, and perhaps new degrees of freedom, combine in different combinations that we'll call propagation eigenstates. This is very similar to neutrino mass mixing, that are combinations of the new degrees of freedom. So when gravitational waves cross through a gravitational lens in these theories, these propagation eigenstates might travel at different speeds. And this has detectable effects on the waveform that can be observed with no electromagnetic counterpart, so they can affect the shape of the waveform. And I will show that for an example theory, this might even be more constraining than the neutron-star merger GW170817. So the framework is, I will not go into any details, but we basically collect our fields into a vector of fields, including all the components of the metric. We then perturb all these components and expand in WKB type of approximation. So we expand in frequency, in a phase and an amplitude, and the amplitude have different corrections that come at different orders. Using this epsilon, this artificial order parameter to order the expansion. Then the tricky part is that there's most of the components of the metric are not actual degrees of freedom. So we need to fix the gauge and solve the constraints until we end up with 3 propagating degrees of freedom. That is the 2 polarizations of the metric and the perturbations of the additional degree of freedom due to modified gravity. And this leads to interesting phenomena in which, for example, the spatial trace of the metric can be sourced by the gravitational wave polarizations contracted with the background scalar field and also the scalar field perturbation. This is not something we call it gravitational wave shadows, but I will not get into detail. So at leading order, and this means really just the causal structure, so only looking at the phase evolution, in a large number of theories, we can write the equations for the dynamical degrees of freedom in this matrix form, where the structure is there is a matrix and each coefficient is a second derivative operator. And I'm normalizing the field so the diagonal terms are have coefficient unity and are characterized just by a speed of the in the wave equation in this derivative operator. And the non-diagonal terms are also characterized by a mixing coefficient. And here I'm making some assumptions of the theory. This matrix might be even more general. But under this assumption, so that it's valid for a general class of theories that I'll mention later, the only one of the metric components couples to the scalar field through this non-diagonal term. Here I'm defining the gravitational polarization so that only the plus polarization is in the mix with the scalar field. And this equation can be solved exactly, producing three different propagation eigenstates. So diagonalizing this matrix, we find three eigenstates. The first one is a pure metric eigenstate, which with my conventions corresponds to the H cross term that, not surprisingly, propagates to at the speed of gravitational waves, CH, whatever speed enters into this derivative operator. There's also a polarization that is mostly metric. So it would correspond to the plus polarization in the limit in which the mixing with the scalar field is 0. But if this mixing term is non-zero, this state carries some of the scalar field perturbation. And most importantly, its speed is slightly different from the speed of the metric perturbation. And finally, there is another polarization, which is the mostly scalar polarization, which is in the limit of no mixing, would correspond to just the scalar field perturbation. But it's also, in the general case, it includes, it carries some of the metric perturbation. And it also has a speed that is modified with respect to the putative scalar field velocity. So with this in mind, let's discuss phenomenology. The main effect that we're talking here is birefringence. So we have different propagation states that travel at different velocities. And this is similar to how certain crystals and certain materials allow the different polarizations of light to travel at different speeds. And this affects the time travel and affects also the light bending. So in our case, we have 4 signals. Recall we also have an electromagnetic signal that might be emitted and detected, and 3 other propagation eigenstates, of which I will not consider the scalar or mostly scalar perturbation. I will just focus on the 2 metric or mostly metric eigenstates. So this leads to 3 time delays that we can define, 3 independent time delays that we can define between these eigenstates. So one will be the ones that are most interesting is the multi-messenger time delay. That's the difference between electromagnetic signal and the metric, pure metric signal. And also there's going to be a polarization, gravitational polarization time delay, which is the delay between the pure metric and mostly metric gravitational polarization. And that's also one that I'm going to discuss. Now, there's also time deflection that it's in general, we expect it to be much smaller than in GR. So I'm not going to discuss this further because time deflection is very hard to measure. Like angular resolution is very small for gravitational waves, but this will also contribute to the time delay. The time delay will be a combination of a Shapiro time delay as the gravitational wave passes near a gravitational lens, time delay will be an integral of the over the velocities, and there's also a geometric component, as these different polarizations or eigenstates could be deflected by different angles. Now, nice thing about these polarization time delays is I'm going to focus on the delay between the two gravitational polarizations, is that this leads to signatures that can be detected without an electromagnetic counterpart. So if the time delay is small, so it's smaller than the duration of the signal, for LIGO this would be smaller than order second for a typical, or half a second for a typical black hole merger. We are in a regime in which we receive the two polarizations at the same time in the detector, and they generate some interference pattern in here. So this is showing for 5 milliseconds time delay. It's a subtle effect. If the time delay is 50 milliseconds, so significantly larger, then we have a pretty more obvious effect on the waveform, where there are features and there is a repeat of the merger phase. There are features in the spiral and a repeat of the, a very clear repeat of the merger part of the signal. And we call this the scrambling regime. We think that this should be fairly easy to rule out with a given gravitational data, but we need to assess more carefully the degeneracies with binary parameters. Now, if this time delay, this could be much larger, then we could enter into the echoes regime, in which the two polarizations come entirely separate, and this separation might be of order seconds, so we would have a very concatenation of events that would look similar in some way, or this could be much longer. This time delay could be years, in which case the signature would be of a statistical nature, and one would need to be address this more carefully. Now, to finish, I just want to show some examples of how these time delays can be computed in a particular theory of gravity. So I'm going to look at these quartic Horndeski theories. This is the Lagrangian. It's a two-parameter theory, and very importantly, this theory is constrained very strongly by the speed of gravitational waves after the neutron-star merger. So I'm going to be focusing only on models that survive that constraint, which puts a very stringent limit on this combination of the parameters. So for a large point mass, we can compute the time delay associated as a function of the impact parameter. And you can see the blue line here is the multi-messenger time delay with respect to the electromagnetic counterpart. It can be of order milliseconds, so it's hard to observe. But the time delay between the two polarizations can be of order milliseconds, which is the regime where LIGO would hopefully be able to detect it. And it can be much larger for smaller impact parameters. So this is in principle a theory that where we can go beyond the constraints already in place from the neutron-star merger 1708-17. And in this diagram, I'm showing the two parameters of the theory. The gray line is what would be ruled out already by the neutron-star merger. And the orange line is what could be ruled out by the time delay between the different polarizations, which goes much farther in parameter space. Now, the trick here is that the impact parameter for which this would be achieved is very small. So one would need to either find a source that is very deep within a lens, so near a massive black hole, or that is very lucky, very well aligned with such a lens. This is difficult, might be unlikely, but it's not impossible. So just to summarize, we've presented a framework for lensing of gravitational waves beyond GR at leading order that has to do with causal structure. The main effect here is birefringence and leads to time delays between the metric and electromagnetic signals, and also, and this is the novel effect, between the two metric polarizations. there is a superior time delay that can be observed on any lens. We don't need to, so this can be observed by a lens very close to the observer or very close to the emitter. And there's also a geometric time delay that I don't have time to explain that can lead to an even larger time delays, but might be also be less likely. And this is it. There is plenty of time of further work to do that we will be doing in the future. So happy to discuss more, and stay tuned for the paper in the coming weeks. Thanks for listening.